Look at question 2 on the homework for the first part of this video, and it asks us to rank these three circuits in terms of their fastest to slowest operation. And the way we're going to do this is use this equation that we derived in class that relates the rate of change of voltage in a circuit to, or rather, this is kind of from the equation of a capacitor, relates the rate of change of voltage to the current and to the capacitance, the ratio between them. And so specifically with the current, we'll be looking at the current being driven into a node V int on each of these circuits. And then we'll also have to look at the capacitance that is present on those nodes. And so we're given assumptions in the problem that each inverter drives at its output a current of I, and that each inverter has an output capacitance of C and an input capacitance of C. So using these two assumptions, we're going to look at circuit 1 first. And we can see that there's two inverters supplying current to this V int, and they both supply a current I. So there's a current I being supplied here. Oops. And a current I being supplied here. We also have to take into account capacitance on this node. And we get that the output capacitance on this top inverter is C. There's also an output capacitance of C on this bottom inverter. And then finally, there's an input capacitance on this third inverter here. And so we can now apply the equation we have at the very top and say that the rate of change of circuit 1 is, let's total up our current going into the node, which is 2I, as well as the capacitance on that node, which is 3C in total. Now let's apply a similar approach to this circuit 2. We can see that the first inverter is driving a current of I into V int. So let's go ahead and mark that down. And then we can also see that this inverter has an output capacitance C, and that the second inverter has an input capacitance of C. So now we've sort of totaled up all of our important variables. We can develop our expression now, that dV dt for circuit 2 is the total amount of current going into the node, which is I, over the total capacitance at the node, which is 2C. Now finally, let's look at circuit 3. We have one inverter that's supplying current into the node under question, which is that first inverter. So I'll say that there's a current I being driven into that node. We have to take into account the output capacitance of that first inverter, which is C. And then we have two inverters at the other end of the node, each with an input capacitance of C. So we've developed the total current and total capacitance for that node, and that gives us all the information we need to determine that dV dt for circuit 3 is, you have 1I going into the circuit and 3C capacitance on the node, so you get I over 3C. So now we have all the information we need to rank them. And so clearly we can see that 2/3 I over C is bigger than 1/2 I over C, which is also bigger than 1/3 I over C. And the bigger this value here, that's saying the greater the rate of change, the greater the speed at which the voltage changes for that circuit, which leads us to conclude that circuit 1 must be the fastest, circuit 2 must be the middle speed, and circuit 3 must be the slowest. So that's how we do that problem. The second part of this video involves talking about a current-starved ring oscillator. And so to enter into this discussion, I'll first just explain how the oscillator portion works, and then I'll go into a little bit more detail about how the current-starved component comes in. So here we have a schematic of a ring oscillator that I built. It contains 33 inverters, which is an odd number, which is actually required in order to create a ring oscillator. So let's say we put a logic 0 on this node here, and we let that propagate through the circuit. Since it's going through an odd number of inverters, its logical inverse will appear on the output of this last inverter. So it went from logic 0 and it came out as logic 1. But since these nodes are connected, the value here on the input will then switch to a logic 1, and it'll propagate through the circuit again. But then it'll come out as logic 0, and this value on the node will change again. So if we just probe at this node, we'll be seeing oscillations between a logic 1 and a logic 0. Now, we also have to take into account the propagation delay that exists on each of these inverters. So that's basically the low to high and high to low propagation delay. We can actually determine the frequency of oscillation for this VCO by looking at the propagation delay, because basically a value on this node will persist the whole time that the signal under question is propagating through the circuit. So if we know the propagation delay of one of these inverters, we can multiply that by the number of inverters that are present in the circuit, and that'll give us the time it takes, or like the time that a single value will persist on this node, which actually also corresponds to half of sort of one period. So you can basically take the propagation delay of an inverter, multiply it by the number of inverters in the oscillator, and then multiply that by 2, and that will give you the period for this oscillation on this node, and then you can take the inverse of that to get the frequency. So that's how the oscillation portion works. Let's look at the current starved inverter itself to get an idea of what the current starved portion means. So you can see the top 2/3 of this circuit is a CMOS inverter, standard like we've been seeing it. But now we've added an additional NMOS between Vout, the first NMOS of the inverter, and ground. And we've actually allowed for an independent gate voltage to be applied to this NMOS. What this does is, before, if we just had the inverter, we would get a fixed current discharge to ground when this input changes from, what would that be, low to high, I believe. What we can do now is we can actually limit the current that's being discharged to ground with another NMOS. And we can do this by modulating this voltage on the gate. And if you think about the current equations, they're dependent on the gate voltage, and so we can either heighten or lower basically the current that's running through this transistor using this voltage. So it kind of acts like a little dial, in a sense, that lets you draw more or less current. Now, what does this really do for us? Because we know how it works now, what's the point? Well, if we remember from the first problem, we defined the rate of change of voltage to be the current over the capacitance. So if we can actually control the voltage here and control the current through, we can actually control the rate of change of the voltage here, which is a translation of the propagation delay, essentially. And so what we can do with this voltage is we can actually make the propagation delay smaller or larger per inverter in this oscillator. And what that means when we think about it from the oscillator's perspective is we're actually changing the frequency of the oscillation on this node here. So if we apply this as a clock, we can actually change the frequency of the clock as it operates. So that's basically how this circuit works. That should cover all the ground that we needed to cover, and I hope you enjoyed.